Welcome back to Wood Engineering. I'm Jeff Roachko from Carleton University, and in this video we're going to take a bit more of a macroscopic look at wood connections. In the previous video we looked at connection types, like what are basically what are the fasteners. And in this video we're going to look at some examples of what the connections actually might look like for different situations. So let's dive right in. All right, so for example, I'm going to start with, if I have a beam sitting on masonry, what are the things that I need to consider? We'll look at beam to beam connections. We'll look at beam to column connections. We'll look at column to foundation connections. Just a few examples and some pitfalls to avoid. Now, one of the big things in connection design is that we want to avoid having our wood members get consistently wet, right? So one of the big considerations there is if I am connecting a wood member to concrete or masonry, those materials are like sponges for moisture, right? And so if I have wood directly in contact with masonry or concrete, then moisture can easily wick through from the concrete, from the masonry directly into the wood. And that might provide a interface where it is often or always wet or moist, which means that I could end up with my wood connections basically rotting away. So in order to avoid that problem, I want to provide a moisture break in between the concrete or masonry and the wood itself. And easy way to do that is just to have a steel plate at the bearing location. So you can see in all three of these connections, I have a wood beam. Sitting on here is some concrete, and in between the two, I have a steel plate at the bearing location. And then I can hold that beam in place using kind of some simple angle brackets. So these are some angle brackets. This is the angle bracket on top of the steel plate. This is the steel plate is a bit smaller, basically same idea. And I have some bolts cast into the concrete, or if I don't cast these in, that's fine. I could also use, adhesive anchors to connect down to the concrete. The one on the right here, these little lines here, this is indications for timber rivets. So you can see that the line directions are in the same direction as the grain of the beam that's sitting on top. So this is just an alternate situation for if I have timber rivets in case instead of using bolts here, for example. Okay, then what if I have a notch? Okay, so this one on the left, it says not acceptable. What it really means is this is not ideal. I can totally design this beam with this notch. So you can see this beam comes over. It might be a little bit difficult because it's all shades of gray, but this is the line of the concrete wall, and I have a beam, and the beam is notched around the wall. So this might be the situation. I only have a certain height here available to put the beam, but I need a certain depth beam to be able to take a certain amount of bending moment, for example. So I don't need that bending moment resistance at the end. So what I do is I put a notch here, and that allows me to sit the beam on this piece of concrete where I have, I have a specific location where I need the top of this beam to be, for example. Okay, so I can design this. I can look at my shear resistance for tension notch fracture, and I can find the strength. But you remember when we talked about tension notches and fracture shear, we get a really big penalty for designing our beam this way. So we're going to have a very low shear strength if I design it like this, and it's, that's a brittle failure condition as well. So it's definitely not ideal to design a timber connection that looks like this. You'll see we're still providing the steel plate to provide a moisture break between the concrete and the wood. So what's a better way? Bearing is always a better way to transfer load in wood than direct shear. Than shear notch, for example. So what I can do is design a connection where I basically have a plate that overhangs down, and that plate has a little seat so that my notched piece of wood here is really bearing on this seat. Okay, so then I have my piece of wood instead of having to deal with this notch shear. I basically have my piece of wood is sitting directly on its bottom, as we like our kindergartners to do, right? So we're gonna sit our piece of wood like this is much better than doing notch shear. So that's one option, is to design kind of a fabricated connection like this to pick up the bottom of that beam. Another option is, if I can, one option is, can I design that wall so that it has a notch in it instead of the beam having a notch, so that I can bring the entire beam and just sit it right down on top of that wall. If that concrete sill here already exists, that might not be an option, but if all of these are part of a new design, then it would be much better to cut out the concrete than to cut out the wood. One thing that you might not realize is that if I have a diagonal bearing like this, I also effectively have a notch. So the geometry of this is such that if I basically have cut I've cut this out. Let me turn it so we don't have that kind of notch. I cut this out on an angle, and then I have a member that's sitting on an angle, and it's only sitting on a part of this bearing surface, just the part near the end here. That's what we're showing here. It's only sitting on the end of that bearing surface. Okay, so I am very likely to get a split here in just the same way that I would with notch shear. So if I look at it with my straws, which I think will probably illustrate this pretty well, I've cut my end on an angle. So I have an angled connection here at my end. So these are my fibers, right? And if I sit only on this part, I'm still going to get this notch shear problem. I'm still going to be loading my my member in basically tension perpendicular to grain, which is going to cause a split at the edge of the bearing surface. Okay, so that's what's happening here. So I do want to definitely avoid having a connection like this. One way I can do this is to lift this beam up a little bit higher. If I could, I would just lift the whole beam up higher so that I would extend this down and make a smaller bearing surface that is basically the entire bottom of that. That's one way to do it, not shown here. Another way is to make a kind of seated connection like this, where I can actually pick up that bottom as well. So basically here I'm notching the beam and picking up both bearing surfaces here. And of course, another option is cut a notch out of the concrete, like design the concrete to have a lowered kind of sill here for sitting the beam on, so that I don't have to expose the bottom edge of this angled surface and make myself subject to these kind of splits. All of these pictures, by the way, are from the Introduction to Wood Design book from the Canadian Wood Council. Okay, so if I want to connect some joists or purlins to beams, here are some ways I can do it. I mean, the most obvious way that you might think about it would be to just do a kind of side plate connection like we would do in steel, right? Like if I was connecting this to another member here, and both of these were steel, and I was only taking shear, I would probably just connect the flange, right? I would put a plate here, and I would bolt through that plate, and then I would rely on those bolts to pick up the whole shear force, right? That's not such a good design detail in wood. Why? Because if I put some bolts here, and I'm just bearing on these two bolts, for example, and I'm pressing this down, I'm basically loading this beam in in tension perpendicular. I'm trying to split it apart, right? Like if I have a bolt here and I push down on it at the end, I'm trying to pull those fibers apart, which we know for wood is not a good way to do it. So it's almost always better to have a seated connection here. Okay, so I'm bolting to the side of this member. So this is that type of connection that I was just talking about. So it's not, maybe totally ideal, but for this really deep member, it's got a lot of resistance, and this load is probably not so high for this member. But this connection here is probably taking something like the full shear resistance of this member. So it's much better to have it transfer that load in bearing rather than in bolt shear directly. So that's why there's a little seat here. This tucks underneath the beam and picks it up from the bottom. Then the only bolt that I need here is just to make sure that this beam does not get displaced off of the seat. And then this little clip at the top is to prevent rotation of that beam, because you remember I have to provide lateral restraint at the top and the bottom of the beam. Okay, so that's what this is. But you'll notice that at the top here, it's not bolted, okay, to allow the shrinkage and expansion of this beam due to moisture, right? So I'm only connecting it in one place here, and then if this whole thing wants to move up and down, it can. Okay, so an even better detail than this one, because here I'm bolting to the side of this big member, is to have this kind of saddle connection here. So this beam is sitting on another beam, or it's loading this other beam, right? So I have one beam framing into the other. Okay, this one is going down relative to this one, right? So this is like our boundary. Okay, so this one is going down, so I have to pick it up on the bottom. That's what this bottom seat is. And at the same time, how do I transfer that load into this beam, right? I can put a plate over the top of this beam because, you know, this is pulling down relative to the beam and wants to pull this beam down, which means I would want to load the top. Okay, so if I can load both of these beams in using bearing, compression perpendicular to grain, then I'm going to get a lot more strength and reliability than if I rely on bolt shear. So that's why I'm loading the top of this beam with this beam, and I'm transferring the load to this larger beam from these joists using this saddle. So the load path is from this beam into this bearing plate, which then gets transferred up through this steel plate onto the top, and then the load here is pushing down on the big beam. Okay, for a purlin that's sitting on top of a beam or a joist, then we only really need to keep it in place because the bearing surface is direct wood on wood contact between the two. So that's what those clip angles just keep it in adequate place. Okay, what about some splices? The one on the left is a moment splice. So I take two pieces of wood here and I want to make it so that I connect them basically for moment, so that I can't have an open up here and an open down here. If I was doing that in steel, I would probably put, obviously I would put a plate over the top and a plate on the bottom and probably weld it all together. Or if I was using a bolted connection, I would put plate top, plate bottom, and probably a big plate on the flanges, or sorry, on the webs as well. We don't want to use big plates here because imagine I put a big plate that was this entire size and I connected those together with bolts, then I would have a shrinkage problem, because if I have bolts top and bottom and those bolts are connected by a steel plate, like they are held in place by a steel plate, that steel plate will not expand and contract due to moisture, but the wood that's behind will want to contract due to moisture. So if my moisture content goes down, then my wood is going to want to shrink in between those two bolts, which means that it is going to basically make a tension perpendicular stress across between those two bolts, which is going to want to crack that piece of wood apart. So it's better to separate those. So I have one set of plates on the top, one set of plates on the bottom. Now, if this wood wants to expand and contract perpendicular to grain, it's perfectly happy to do so. Just means, you know, this plate will get closer to this plate, or this plate will get further away from this plate, but there's nothing restraining that movement. Okay, here you can see there's some shear connection in the middle here that I didn't talk about. This could be, for example, shear plates. It looks like these are all shear plate connections, actually, the way that these are drawn. So that's a possible way to connect those. We talked about shear plates in the previous video. Okay, let's say that I have a cantilever beam here, and this is sitting out, and then I want to sit another beam on the end. Like I want to take another beam here, and I want to have it sit and be supported by this cantilevered beam. Okay, so I have another beam here, I want to support it on the end of a cantilevered beam. How would I do that? That's what these other two connections are showing. This is a way to do that so that I'm totally relying on bearing forces to transfer that load. So here, this is the one that's the cantilever beam poking out. This is the one I want to sit on top of it. So the load path is this beam, the load is going to go into the bottom surface because it's sitting down on that bottom surface. That load is going to be carried up the side in tension and transferred to this top plate, which is then going to sit on top of this cantilevered beam portion. Okay, and this is a similar detail, just using a collar type of detail instead of this one. So here I have flat ends on the beam. This one I have to taper, I have to angle the end of the beams in order to accommodate that connection. These are you're probably not going to run into this too much because it's not very common to try to do moment connections in timber. And I mean, you might have multi-spans where you have a cantilever and then another one sitting. That could be possible. Okay, so let's say I have beams sitting on top of a column. So I have my column here, and I have my beam sitting on top. You know, the load is being transferred in bearing between the beam and the column. There's a bearing surface at that interaction there. But how do I keep these in place? You know, I want to keep them so that, you know, this is not going to tip over. So I want to connect it to the adjacent beam. And I also want to make sure that this beam doesn't become unseated from this column. So I need some kind of connection. Okay, so the one at the left, you can imagine why this is not acceptable for the same reasons that we just talked about, because here we have two bolts which are separated by quite a large distance, but the steel plate restrains the movements of those bolts. So those bolts will always be that exact distance apart. So then if the beam behind wants to shrink or expand, it's going to induce perpendicular to grain stresses, which could cause cracking of this beam, which would not be desirable. So basically, the easy solution to that is don't put a big plate, separate the plates. And here you can see there's even slots provided to ensure that there is some allowance for these beams even to expand and contract longitudinally, especially if they're long. That would be a good idea. Okay, these are just a few other examples of, you know, how to connect beams to the top of columns using steel collars. These are all acceptable kind of situations. Again, typically we want these bolts typically to be about as low as is reasonable when I'm talking about perpendicular to grain shrinkage, because I don't want this to shrink up and then crack. But these are just welded plate connection here. Here is a clip angle connection. So basically I'm providing support for the bottom using this angle, some bolts here, and these are lag screws, and then keeping these from moving relative to each other longitudinally using single plates on either side. And this is a full up welded up connection where I have a steel column instead of a timber column. I'm just using a manufactured connection to keep everything together. Okay, so now when I have a column coming down to the base, I have the same problem that I did before when I was looking at beams sitting on concrete. So here I have a column coming down to a foundation. Just like before, I don't want my timber to be in direct contact with the concrete if I have the concrete foundation here. Okay, so I mean, that's one thing that's kind of obvious because, you know, I'm going to provide a plate. I could provide a plate here and then sit this on top, and then they're not in contact, and that's fine. Right, and then I can provide clip angle. I can provide some angles to hold it in place, which are, you know, with bolts cast into the foundation or whatever. But something that you might run into a problem then is, you know, often if I have a steel column coming on top of a concrete foundation, then maybe I want to pour a slab, like a slab on grade, for example, around that column. And now I'm going to run into the same problem, because now if I cast this slab on grade around the column, now the column is going to be totally engulfed by concrete, which means long term, this thing is going to stay pretty wet. And, you know, like moisture is going to wick up from the soil through the concrete into this timber, and it's going to just rot out. Then you're not going to have a bottom for your column anymore, which is a very naughty thing to do. So you got to avoid doing this. You don't want to cast this all around. So if you're one option is if you are restrained geometrically, like, you need this column to come down a certain depth. One option here is to provide this collar. Of course, another consideration if you're doing a collar like this is you have to provide some space for water. If water gets stuck in this column, it has to be able to flow out. So you can't make like a closed collar on the bottom of a steel column, because inevitably water is going to get in there. It's going to get stuck, and then it'll rot your column. So you need to provide always some kind of weeping space to allow water to get out. So this is not a great, probably not a great deal. A better detail is to just extend up the foundation a little bit and make sure that your column is sitting on top of it without casting a bunch of concrete slab around it. These are just another couple example details that you can use. This one is pretty interesting on the right because it basically hides the bolts that are holding down the column. So basically the steel plate is held into the concrete using these cast in place bolts. The steel plate then comes up the side of the concrete column just to hold it in place with this one bolt. and the connection down is hidden by the timber itself. So you would have to drill out some space for the nut and the end of the bolt. And then you probably get a kind of neater looking connection. But this is fine too. I mean, it depends on what your aesthetic requirement is. Okay, now what about hanging something from a beam? Okay, you might have some occasion certainly to hang some things from beams at some point. Now, you know, you might be tempted to do something like this. Certainly, I mean, neither of these is really the ideal detail for this, but let's say that I did want to bolt into the side of a member in order to hang something from it. So I have a bolt through here, and I'm basically hanging from that bolt. I have something hanging down below, something structural, for example, hanging down from below. Say I'm picking up a walkway or something. Okay. What we'll learn when we talk about tension perpendicular, which is basically what this load case is, it's going to try to split the wood, is that when I do that, I want to locate the bolt as high up on the member as possible, because in that splitting load case, like in that splitting resistance, it's this distance between the bolt and the bottom of the member that determines what the strength is. So if I locate my bolts really low on the member and I try to hang from here, I'm going to have a much, much lower strength than if I try to hang from higher up on the beam. So that's what this is just showing. You know, you want to avoid this. You'll be less likely to get splitting if you hang it up higher. Even better, put it over the top, put the plate over the top, and transmit that load in bearing instead of transmitting it like this. But you know, you might not always have access to the top of a beam. Maybe there's something already on top of it. So that's it for some tips for connection design. In the next video, we're going to talk about some kind of details about geometry and common things that we need to think about when we do connection designs before we get into the detailed design of nailed and bolted connections.